When we're first taught about chemistry in school, there's this very comforting expectation of order. It's almost presented like atomic Lego blocks.
Oh, totally. Very neat and tidy.
Right. You take a sodium atom here, a chlorine atom there, you just snap them together, and you get table salt. It's binary, it's clean, and most importantly, it feels highly predictable.
Which is great for a high school quiz, but, not quite reality.
Exactly. So if you're gearing up for a TEAS or HESI nursing exam, or if you're just an insanely curious learner trying to understand how the physical universe actually holds itself together, you need to know that those perfectly snapping Lego blocks are an illusion.
A massive illusion.
Okay, let's unpack this. Because that high school textbook version of chemical bonds is actually a huge oversimplification. And in some cases, it's literally a century-old lie.
I love that phrasing because it really is. Today, we have to move past just, memorizing flashcard definitions. We aren't just looking at what a bond is. We're looking at why atoms behave this way.
Because it's a messy, dynamic dance of probabilities, right?
It is. And that underlying physics, it dictates everything. I mean, from the physical texture of the pencil you're holding right now to the specific electrical impulses making your heart beat at this exact second.
Okay, before we can even get into how atoms connect or share or steal from each other, we have to establish why they would ever bother interacting in the first place.
Right, the fundamental motivation.
Yeah, because you hear this phrasing constantly in introductory classes that atoms want a full outer shell of 8 electrons.
Oh, I hear that all the time.
It almost makes them sound like they have some sort of conscious atomic checklist they are trying to complete. Like, do atoms actually want 8 electrons?
Yeah, that framing is a major hurdle for a lot of people. Atoms absolutely do not want anything. They don't have desires.
So no atomic bucket list?
No, definitely not. What we're actually observing is just basic physics. Specifically, it's the universal drive toward achieving a lower energy state.
So it's not desire. It's more like, laziness.
Yes. A system will always naturally settle into its lowest possible energy state. An atom with an incomplete outer electron shell is in a higher energy, highly unstable configuration.
Like a tightly wound spring.
Exactly like a wound-up spring. It's tense. When atoms bond, they rearrange their outer electrons, either by giving them up, taking them, or pooling them together.
And doing that just drops the total energy.
Right. That spatial rearrangement drops the total energy of the entire system. The bonded state is simply more relaxed and stable than the unbonded state.
Okay, but here is where human intuition will trick you. And it's exactly why so many people get this wrong on their exams.
Oh, the energy trap.
Yes, the energy trap. Because we hear the word bond, we intuitively think of something containing or storing energy. So the gut reaction is to assume that breaking a chemical bond releases energy.
Like setting off a microscopic biological explosion.
Right, but that's wrong, isn't it?
It is completely backwards. Breaking a bond never releases energy. Breaking a bond always requires an input of energy from the outside. It is an endothermic process.
Endothermic, meaning heat or energy goes in.
Exactly.
I always picture two incredibly strong magnets stuck together. When they are connected, they are just resting in a stable, low-energy state.
They're perfectly happy there.
Yeah. But if you want to pull those magnets apart, you have to do physical work. You have to sweat a little bit and put your own energy into the system to force them apart.
That's a perfect analogy.
But if you let them go, they snap back together on their own, and they release energy when they connect.
Forming a bond always releases energy. That's exothermic. Atoms bond because it allows them to dump that excess unstable energy out into the universe and finally relax.
Let's look at the poster child for the ionic bond to see this in action. Sodium chloride, regular old table salt.
The classic.
The math behind how these two atoms interact is frankly violent.
Oh, it really is. It's intense.
Yeah.
You start with a sodium atom, right? It has this one lonely electron sitting way out in its outermost shell, and the nucleus holds onto it very weakly. It only takes about 496 kilojoules per mole of energy to rip that outer electron away completely.
It's essentially leaving the front door unlocked with the keys in the ignition.
Pretty much. Then you have chlorine right next door. Chlorine is missing just one single electron to complete its outer shell, and its nucleus attracts surrounding electrons super aggressively.
So it just snatches it.
Right. And when chlorine snatches that extra electron, dropping into a more stable state, it releases about 349 kilojoules per mole of energy.
Wow.
So sodium hands its electron over, becoming a positively charged sodium ion, a cation, and chlorine accepts it, becoming a negatively charged chloride ion, the anion.
And because one is suddenly positive and the other is negative, they snap together through electrostatic attraction. It's just atomic scale static cling.
Yeah, but it doesn't just happen between two isolated atoms. That's the wild part.
What do you mean?
Well, each positive sodium ion powerfully attracts multiple negative chloride ions around it in all directions, and vice versa. They construct an enormous, repeating three-dimensional grid called a crystal lattice.
Oh, like a massive scaffold system.
Exactly. And the energy locking that entire structure together, which is known as the lattice energy, is a massive 787 kilojoules per mole.
Which explains why table salt doesn't just melt on your kitchen counter on a hot day.
Not at all.
It takes a staggering 801 degrees Celsius just to melt salt. And
Yeah.
temperature is just atomic motion, right?
Correct.
So you have to heat that salt up to 801 degrees just to get the atoms vibrating violently enough to finally break that massive lattice energy and pull apart.
It's incredible.
That is wild when you realize it's made from sodium, which is a soft metal that explodes upon contact with water
Yeah.
and chlorine, a highly toxic green gas.
But their dangerous individual properties just vanish the moment they drop into that stable, low-energy bonded state.
Okay, so if sodium is an easy target for chlorine, what happens when you have two identical atoms that are equally matched? Let's say two hydrogen atoms. Neither one has the pulling power to outright steal an electron from the other.
This specific scenario was a massive puzzle for early 20th century chemists. The resolution to it actually involves a truly fascinating historical coincidence from the year 1916.
1916?
Yeah. So Walter Kossel proposed the electron transfer idea we just explored, the ionic bond. He analyzed noble gases like helium and neon, which are totally unreactive, and reasoned other atoms must be physically transferring electrons to copy that stable arrangement.
Makes sense based on what we just talked about.
But Kossel's theory totally failed to explain molecules like H2 or Cl2.
Because in a tug of war between two identical clones, nobody wins.
Exactly. But in that very same year, 1916, Gilbert N. Lewis published his landmark paper introducing the covalent bond.
Oh, wow. The same year.
The exact same year. He theorized that instead of transferring an electron, two equally matched atoms could each contribute one electron to form a shared pair.
And they share it equally.
Right. That shared pair sits right between both nuclei holding them together. They basically pool their resources.
They both published the foundational theories of the two main bond types in the exact same year, decades before quantum mechanics could mathematically prove why any of it actually worked.
It's pretty amazing. They arrived at the right qualitative picture purely through observation and logic, long before the rigorous math existed to justify it.
But they laid the groundwork, and yet the binary way we teach their discoveries today is really flawed, isn't it?
It's very flawed, yes.
Here's where it gets really interesting. We've set up these two neat boxes. Ionic means transferring electrons, covalent means sharing electrons.
Right, the classic boxes.
But that clean line is a total myth. We are taught it's either a light switch turned on or off, but in reality, it's a dial.
It really is a dial. Linus Pauling revolutionized this in the 1930s with the concept of electronegativity.
Electronegativity, let's define that.
It essentially measures how strongly a specific atom pulls on shared electrons. And he actually won the 1954 Nobel Prize for showing that bonding is a continuum.
A continuum, so it's not just shared or stolen, it's everything in between.
Everything in between.
I read that even table salt, NaCl, the textbook example of a pure ionic bond, actually has about 30% covalent character.
It does. The electrons aren't 100% transferred. They are heavily lopsided in their sharing, spending the vast majority of their time orbiting the chlorine nucleus. But they still spend a tiny fraction of their time around the sodium.
So instead of it being either a perfectly equal joint bank account, which would be pure covalent,
Right.
or outright wallet theft, which would be pure ionic, it's more like a joint bank account where one partner unilaterally spends 99% of the money.
That is exactly how you should think about it. By Pauling's rough guideline, if the difference in electronegativity between two atoms is greater than about 1.7 on his scale, we just categorize it as ionic to make the math easier.
Just to simplify things.
Yeah. But in reality, almost no bond is purely ionic or purely covalent.
Okay, so now that we know bonds exist on this lopsided sharing spectrum, how does that unequal sharing actually dictate the physical properties of the world around us? Let's talk about water, H2O.
Water is the perfect showcase of polar covalent bonding. Oxygen and hydrogen share electrons, making it a covalent bond. However, oxygen is significantly more electronegative,
It pulls harder.
much harder. On the Pauling scale, Oxygen is 3.44 and hydrogen is only 2.20.
So oxygen is the partner spending most of the money in the joint account.
Exactly. The shared electrons spend way more time orbiting the oxygen nucleus than they do the hydrogen nuclei. So it's not a neutral molecule.
Right, the charges get skewed.
Yep. The oxygen end takes on a slight negative charge, and the hydrogen ends take on a slight positive charge.
We call that a polar covalent bond. It has poles, like a magnet.
I've got it.
But here's another spot where human intuition tricks us, and it's a major exam trap. We tend to visualize water as a straight line, an oxygen atom in the middle with a hydrogen pointing straight out on each side.
But water is physically bent.
Right.
It's bent at exactly 104.5 degrees. It is not a linear molecule. Oxygen actually has two pairs of outer electrons that aren't involved in bonding with the hydrogen at all. We call them lone pairs.
Lone pairs.
Okay. And because all electrons are negatively charged, they fiercely repel each other. Those lone pairs on top of the oxygen atom physically push the hydrogen atoms downward, bending the entire molecule.
And that bent shape, combined with those polar charges, fundamentally changes how water behaves.
Oh, completely.
It means the slightly negative oxygen of one water molecule acts like a magnet, attracting the slightly positive hydrogen of a completely different water molecule next to it. They stick together.
We call that hydrogen bonding. It explains why water has an unusually high boiling point for a molecule of its size. You have to break all those magnetic attractions to turn it into a gas.
That makes a lot of sense.
It explains surface tension, too. It explains why water is the universal solvent that can pull apart other molecules, making biological life possible.
And it all traces back to a 104.5-degree angle. That is mind-bending.
It really is.
But let's shift gears and look at pure covalent bonds, where the sharing is completely equal. Take diamond and graphite. Both are 100% pure carbon. How can the hardest natural material known to humanity and the soft, crumbly lead inside a pencil be the exact same elemental building block?
It purely comes down to bond arrangement. In a diamond, every single carbon atom forms 4 incredibly strong covalent bonds to 4 neighboring carbon atoms, creating a rigid, 3-dimensional tetrahedral network.
So they're all locked together.
Exactly. The entire diamond is essentially one giant, continuous molecule locked in all directions.
There's no weak point.
None. But graphite is different, which is why we use it to write.
Right, graphite smudges.
In graphite, each carbon atom only forms 3 strong covalent bonds. They arrange themselves into flat, 2-dimensional hexagonal sheets, sort of like chicken wire.
Okay, 2D sheets.
And the bonds within those sheets are strong, but the forces holding the sheets together in a stack are very weak. So when you drag a pencil across paper, you are applying enough friction to slide those flat layers past each other.
So they just flake off onto the page.
Exactly.
Which proves that how atoms bond is just as important as what they are made of.
Absolutely.
But wait, what about a solid chunk of iron or copper? We talked about ionic and covalent. The third type of bond is metallic, right?
Right. Metals are unique. They don't transfer electrons, and they don't share them in localized pairs either. Metal atoms release their outermost electrons into a shared, highly mobile sea of electrons.
The sea of electrons.
Yeah, these negative electrons drift freely around a lattice of positively charged metal ions.
And that delocalized sea is why metals are so malleable. Like if you hit a piece of copper with a hammer, the positive ions just slide past each other.
Right, because the sea of electrons acts like a flexible, moving glue, keeping it all from breaking apart.
Compare that to hitting our table salt crystal with a hammer.
Oh, completely different. The ionic lattice in salt is completely rigid. The electrons are locked in place. If you strike salt and shift the microscopic layers even slightly, you suddenly align positive sodium ions right next to other positive sodium ions.
And like charges repel.
Violently, like charges repel violently, and the whole crystal shatters instantly.
We've built up all these beautiful tidy rules, the octet rule, the neat geometries of molecules. But exams and the human body love to test the exceptions.
All nature loves an exception.
So let's shatter the octet rule. The idea that atoms bond to get exactly 8 outer electrons is taught as absolute law, but our sources call it a historical overreach.
It is probably the most famous overreach in chemical education. It's taught as gospel, but many incredibly stable molecules completely ignore this rule.
Like what?
Well, boron trifluoride only has 6 electrons around the central boron atom. Sulfur hexafluoride has 12. Phosphorus pentachloride has 10.
And these aren't just obscure lab curiosities, right?
No, SF6 is heavily used to insulate modern electrical equipment. But honestly, the most interesting exception is nitric oxide, NO.
Why is that one special?
Nitric oxide has an odd number of total electrons. That means there's one unpaired electron just hanging out, and even an octet is mathematically impossible.
But it's stable.
Yes, and not only is it stable, it's a critical signaling molecule that dilates blood vessels in the human body. Its discovery as a biological messenger actually won the 1998 Nobel Prize in Medicine.
Wow.
It proves the octet rule is just a useful heuristic. The real underlying law of nature is always just achieve the lowest total energy state, regardless of how many electrons it takes to get there.
Which brings us to a genuine scientific rivalry from the 1930s over how to even conceptualize these bonds.
Oh, yes.
You had Linus Pauling pushing valence bond theory, which is the classic idea of localized overlaps between two specific atoms.
Wow.
And then you had Robert Mulliken and Friedrich Hahn pushing molecular orbital theory,
Mhm.
arguing that electrons exist in delocalized wave-like clouds spread across the entire molecule.
Right, and both theories survive today because they are useful for predicting different things. But Mulliken and Hahn's molecular orbital theory predicted bizarre realities that Pauling's theory just couldn't.
Like what?
For instance, it correctly predicted that oxygen gas O2 is paramagnetic.
Wait, meaning liquid oxygen is physically attracted to magnets.
Exactly. Because molecular orbital theory shows it actually has two unpaired electrons sitting in its outer clouds.
But you wouldn't see that normally.
No, if you just draw the classic Lewis dot structure with a simple double bond, you completely miss the reality of those unpaired electrons causing magnetism.
Wait, I have to challenge that image. When we say double bond, my brain instantly pictures two wooden sticks connecting two plastic balls in a chemistry kit.
Everyone pictures that.
But that can't be what's actually happening at a quantum level, right? What physically is a double bond?
Well, a double or triple bond means you have multiple shared electron pairs occupying overlapping orbitals in space.
Okay.
You start with a sigma bond, which is a direct, head-on overlap of electron clouds between the two nuclei. Think of it like two people shaking hands directly between their bodies.
Okay, so that's the first connection. What's the second?
The second connection is a pi bond. Pi bonds form when orbitals overlap parallel to each other, creating electron clouds that sit above and below the main sigma bond.
So it isn't a second physical stick?
Not at all. It just draws the two atoms closer together, making the overall bond shorter and stronger. And importantly, that parallel overlap restricts rotation.
Like trying to spin two wooden boards that are held together by a single nail versus two boards held together by two nails.
Right. The single nail lets them spin freely. The second nail locks them in place.
And that locked rotation is the entire reason we have cis and trans fatty acid isomers in nutrition.
Exactly.
Let's break down what an isomer actually is for anyone without an organic chemistry background. Iso means same, mer means part. An isomer is a molecule that has the exact same chemical formula, the same number of carbon, hydrogen, and oxygen atoms, but a physically different 3D arrangement in space.
And because that double pi bond won't let the molecule twist, the hydrogen atoms can end up permanently locked on the same side of the carbon chain. That's a cis fat.
Okay.
Or they get locked on opposite sides, and that's a trans fat.
And your body cares about that shape.
Very much so. Your body's enzymes recognize that physical shape, which is why trans fats are notoriously difficult for your metabolism to break down.
Human intuition tricks us again here, especially on nursing exams regarding electrolytes. This is a massive HESI and TEAS exam trap. Nursing students often conceptualize sodium and potassium in the human body as if they want to form solid salt crystals in your veins.
Oh, that is a fatal exam error. Conflating the ionic bond in a solid rock of salt with physiological electrolytes is a massive conceptual mistake.
Because they aren't rocks in our blood.
Exactly. In solid-state chemistry, sodium and chloride lock into that rigid crystal lattice. But in the watery environment of your blood plasma and cell fluid, they do not form solid bonds.
And what are they doing?
They exist as separate, freely moving charged particles. They are hydrated, meaning they are surrounded by a cage of polar water molecules, basically keeping them apart.
So what does this all mean for you? Let's bring all these concepts together to look at how this applies to everyday healthcare and biology. Think about a standard IV bag in a hospital. Why do they use saline, which is sodium chloride, instead of sugar water to match your blood's fluid balance?
It entirely depends on the bond types we've been discussing today. Sodium chloride is ionic. When it enters the water in your blood, it completely dissociates into those freely moving charged ions.
And we need those ions.
We do. Your nervous system relies on those moving electrical charges to conduct the nerve signals that make your diaphragm expand and your heart muscle contract.
But sugar is different.
Right, sugar is a covalent molecule. It dissolves in water, sure, but it does not ionize. It holds onto its shared electrons tightly and carries no electrical charge.
This also completely explains how vitamins work in your body. Vitamins A, D, E, and K are fat-soluble. They are primarily large, nonpolar covalent molecules.
Yes.
Because they are nonpolar, they dissolve perfectly into the nonpolar fatty tissues of your body where they can be stored for months. Vitamin C, however, is a highly polar covalent molecule.
Right, so it dissolves rapidly in the polar water of your bloodstream, meaning your body flushes out the excess almost immediately. It's the exact same chemical principle that dictates why oil and water never mix.
Because polar covalent water molecules act like magnets.
Exactly. They are heavily attracted to each other, so they physically squeeze the nonpolar oil out of the way.
It's why tossing ionic salt on an icy sidewalk melts the ice. The charged sodium and chloride ions physically wedge themselves between the water molecules, disrupting that hydrogen bond network and preventing the water from freezing into a solid crystal.
It really all traces back to how these atoms share or steal electrons to drop their energy state.
It all comes back to that structural foundation.
And considering all of this, I actually want to leave you with one final thought based on our sources.
Let's hear it.
We established earlier that water is a polar molecule, specifically because it is bent at a 104.5-degree angle.
Right, those lone electron pairs on the oxygen atom repel the hydrogen atoms downward, creating a distinct positive end and a negative end.
And that resulting polarity is what allows water to stick to itself, to form liquid droplets, to maintain a high boiling point, and to act as the universal solvent that allows cellular life to function at all.
It's a prerequisite for biology.
Exactly. So consider the alternative. What if oxygen's lone electron pairs didn't repel? What if water formed a perfectly straight 180-degree linear molecule?
Oh, wow.
The positive and negative charges would pull in exact opposite directions and perfectly cancel each other out. Water would lose all of its polarity.
It would just be totally neutral.
Yeah. So in that alternate universe, would liquid water, or biological life as we know it, even be able to exist?
That is a staggering thought.
We've gone from talking about simple atomic Lego blocks to the very subatomic conditions required for life to emerge.
I definitely encourage you to ponder that structural butterfly effect tonight. Thank you for joining us on this deep dive into the literal bonds that hold our reality together. Stay curious,